Okay, so here we are looking at deformation of solids. I think this is video 4. So we're going to expand on Young's modulus formula. Remember, the Young's modulus formula was E equals your stress divided by your strain. Okay, so now if we're going to expand it, let's put in what those actually are. So E could also be the force divided by area, which is stress, over your extension divided by original length, which is your strain. And rearranging that, you get FL over AX. This is a good formula for when you do multi-choice. You might find that when you do multi-choice, you might get a question about what happens if we have 2 times the area and 2 times the force. What will happen to the Young's modulus? This is an easy question, so let's have a look. If you have FL over AX, we're going to have 2 times the area, 2 times the force. The 2's will cancel out, and you're left with the same E, same Young's modulus. However, we could try a bit harder one. If you think about that question worked because I was not changing the material. Remember, Young's modulus is for the material. Okay, so if I don't change material, the Young's modulus should not really change. So questions that are more likely will be, how does the extension change depending on if I double the diameter and have, let's say, half the force. And now remember, if you double diameter, you actually have from pi r squared, remember you have, because of that square, you'll actually have 4 times the area. So let's put in the formula 4 down the bottom line there, half at the top line there. Now that actually makes 1/8. Okay, so we got 1/8 FL over AX. Now, how does X change to keep E the same? Okay, so how does X change to keep E the same? Well, it has to be 1/8 of X. Of X, okay, to make it the same. In other words, 1/8 divided by 8 will actually then go to the top line, so it's going to be 8 over 8, which means it doesn't change. So the X will go down 8 times. Now, does that make sense? Let's have a look. If we double the diameter, does that make it easier or harder to stretch? Okay, it actually makes it harder to stretch if you think about that. And we half the force, so then it's harder to stretch again. Okay, you know, we don't get that same sort of extension, so we're getting 8 times less the extension. So that makes sense. And so when you're putting the stuff into this formula, make sure that you use area, please, not diameter. Okay, and then just put this in. That's a mess. Stress and strain graphs, if you follow the graph is linear if you follow the Hooke's law. Hooke's. Okay, so remember that. Labor location of the UTS, that's at the very end. Okay, ultimate tensile stress, that's where essentially where it breaks. Okay, at that point. Label the lines hard or soft material, well that's hard. Greater spring constant or Young's modulus, soft. Area under the line, okay, remember we're doing force over area multiplied by nothing. Okay, so what does that actually give you? It actually essentially will give you, in this case, the energy, okay, stored.